It's a pleasure to be here. So my talk is going to be tropical wave dynamics. So the title says simple models for global simulations. I will show more simple models than global simulations. So there are lots of people involved in this work. And this is like some of this work is very old that I don't remember all the details. So just bear with me. And normally you would see names coming as I will be showing the details. So this is just an introductory slide, a warm up. Most of you are aware of all these things, so I'm not really going to spend too much time, but so you all know that Matsuno is the breakthrough in tropical meteorology. Before Matsuno, nobody really cared so much about doing rigorous work in the tropics. People thought it's chaotic and unpredictable and just live with it. And then, of course, this can, I heard that it was triggered by Yanai, who discovered what we call now Yanai waves when trying to study the QBO in the 60s during the space race. So for now, we know that there are two main circulations, basically types of circulations in the tropics. And like the mid-latitudes where you have UG explains everything. In the tropics, we have like what's known as the barotropic mode. And then there's the baroclinic circulation that usually has the warm core that's adiabatically driven. And we know now that thanks to a lot of work by Nakazawa, Boualem and Khouider, that the tropics are more than just the Matsuno waves. There's tropical waves, what we call convectively coupled waves, and then there's a hierarchy of scales from mesoscales to synoptic scales to planetary scales, like the Madden-Julian oscillation and monsoon intraseasonal oscillations that are basically coupled to each other, and there's scale interactions across scales in both time and space. And that makes it very complicated. And understanding all these interactions across scales and across different types of circulations is one of the big problems in this area, and especially interactions between the tropics and extratropics, and how all these waves and all these different dynamics came into play is one of the most significant problems. So already since Matsuno, there is the work by Gill, where they explain simple things like the Walker cell and the Hadley cell, and how what's known now as the Gill model, which people try to extrapolate it as being the MJO in a way, or at least being some model for the MJO. I'm not saying that. I'm just saying that people do that. And then there is this all Matsuno waves that are used to explain this, and so this become like the modus operandi in this area, to try to use these wave dynamics, which are, we call them the normal modes or the modes by which the tropics basically respond. And like in the mid-latitudes, we have only Rossby waves and gravity waves that are very fast and not really important. But in the tropics, there is no scale separation between the slow Rossby waves and the fast waves, because there is a spectrum of all other waves in between, and then that's what makes it both hard and interesting and complex. So I'm going to try to dive into all these ideas through try to highlight these three topics. The first one, I will try to talk purely in terms of dry dynamics and show how the barotropic and the baroclinic modes kind of interact. and they can explain somehow the tropical, extratropical interactions. And also we'll talk about like shear instability. And one thing new that I'm going to talk about, like how eddy viscosity is actually important in the tropics in terms of actually coupling the waves and making like a pathway for the waves to interact, which is kind of a surprise to me and interesting. And then I will move to moist dynamics and talk about the one thing that has been working on for a long time. It's called the multi-cloud model, which we made it into a parameterization in GCMs and for many years now, and we made a lot of progress in that. But I'm just going to show really how the waves interact and how the baroclinic waves interact to explain some like of these convectively coupled waves that as opposed to the dry waves. And then I will try to talk about convective momentum transport as a means for scale interactions across scales, from mesoscales to synoptic scales, but also from synoptic scales to planetary scales, like from convectively coupled waves to the MJO. So I might not have time to cover all I said I would cover. This is just an advertisement for a book where you can find most of what I'm going to talk about. Okay, so the idealized model we work with is just the dry heterostatic primitive equations, and with the reference scales of synoptic scale dynamics that makes the beta and the stratification to be on the same level. So then you have the both, and that's where the sweet spot is in the tropics. So these are the barotropic and baroclinic modes. So you look at a group that has a much more sophisticated way of figuring out these modes, but this is the poor man's approach, where you assume rigidly binary conditions, where the vertical velocity is zero at top and bottom, and then you write down the linear equations, you expand them in the vertical, you get these vertical modes that are just cosines and sines. And then there is the small one mode that's just uniform in the vertical, that's called the barotropic mode. So that would be the V bar. And then here we select just one baroclinic mode, that's the first mode. So normally you have an infinite number of cosines, so cos k, z, pi, etc. For k going from 1 to infinity. But if we just choose the first baroclinic mode, that's the deepest mode, and actually it's the mode that's believed to be more active in convectively coupled waves and in the MJO. It's not the only mode that contributes, but it's the more energetic. So then if we want to understand how tropics and extratropic interact, we can just look at the barotropic mode and then the first baroclinic mode, and that's what you are doing here. And then you project the nonlinear primitive equations into these two modes, you get these two systems. One will be the barotropic equations, we call them, and one will be the baroclinic equations, which is just Shalawar equations. And then you get the interaction terms between the barotropic and baroclinic mode. This is how the baroclinic mode fits into the barotropic, and this is how the barotropic mode fits into the baroclinic through the advection, but also the advection of the barotropic by the baroclinic, which is some kind of a nonlinearity that becomes like vorticity. So I think I can skip this slide. So if you neglect the interaction terms, you have the Shalawar equations for, this is the Matsuno model for the Matsuno waves, like the barotropic, the baroclinic, Rossby waves, the Kelvin waves, etc. And this is the barotropic mode that's basically just represents waves that are propagating westward in the zonal direction, but they can go north and south. And now, so the idea is that you can have interactions between the tropics and extratropics, because the tropics will excite this kind of planetary waves. The equatorial tropic waves will excite the non-tropic waves and vice versa. And that's, you get tropical, extratropical interactions. So this is probably not all familiar with this diagram. So these are all the lines on the Matsuno waves, and just basically to tell you why they are important. And of course, then there's the Madden-Julian oscillation that doesn't project on any of these waves. And of course, that's a different, completely different lecture and different topic. So now the first exercise we're going to do is just to assume that the barotropic mode is forced by some forcing, that's the some equatorial waves. So then you get that nonlinear interaction term that we have here. We just call it F, but now we're going to assume it's coming from somewhere. So we can rewrite the barotropic equations like this. So we can use the Arakawa-Jacobian numerics and so on. And then this will be the forcing from an equatorial wave. And you can guess we're going to choose a Kelvin wave to force the barotropic equations. And when we do that, we get this as a response. So this is the Kelvin wave that you use the Kelvin wave to compute that forcing, and then how the forcing looks like. Of course, it's trapped at the equator, and that's the response you get, which is not trapped at the equator. And I told you the Rossby waves move westward, and also they move north and south. If you look at Hofmoder diagram, so this is what you get. You get actually that response is moving eastward. Of course, just following the Kelvin wave forcing, but there is also waves that moving westward. So what happens is that your forcing is creating a phase-locked response, which is basically from the forcing. It's here, and that's the Kelvin wave response, and that's how it looks like. Looks like a Rossby wave that moves eastward with the forcing. And then you get lots of other waves. You get actually an infinitely many, but then they get weaker and weaker. So this is the first one. This is like a planetary Rossby wave. And this another planetary Rossby wave that's actually weaker. So that's, there you go. So you have a Kelvin wave, you force the barotropic mode, and you get a response that consists of one kind of Rossby looking like wave that moves with the Kelvin wave, and other genuine Rossby waves that moving westward. And we can write it down, and now we know roughly what the answer should look like. And when we do the math, we extend, we get exactly that. So we get the forced response that comes out, and then we get infinitely many Rossby waves that are Lipsages. The size 0 is the response, and it looks like this. And the other ones are just pure Rossby waves, and then they actually interact with each other. So what happens is that the size 0, which is the forcing, excite the first Rossby wave, and then that Rossby wave cascades to the next, and so on through these terms here that are basically cascading down to the
Is there some linearization involved here?
Oh, there's no linearization. This is basically just we take an ansatz. We think the solution is made up of that forced locked phase locked response, which we call psi 0. And then we have an infinite number of Rossby waves like this. So that's the ansatz. We put this in the equations, and then we derive basically this will cancel because this is the phase locked, which is basically takes the response out. And then you have an infinitely many equations that all have forced by the psi itself, psi zero itself, and also the Rossby waves will be forcing each other. So I, J, so you get these cascades.
Is there some inflow involved, or there is no inflow?
No, the only thing is the Kelvin wave is moving itself. We impose it to move.
How do you separate part of stream function moving eastward and westward?
How are they separated?
Yeah, because you have separation.
Well, this is separated from the simulation. We separated just by using spectral.
Okay, so you do
Analysis.
Fourier gradient in time.
Yeah, this is the spectral power for that simulation I showed. We do the spectral power. You get the, like I say, there are infinitely many. We can make this bigger. You see many of them, but then they go smaller and smaller and smaller and smaller. And of course, in reality, you probably see only the first one. This one is already weak. Like you see this 10 to the minus 4 or something here, a 3, and this is 10 to the power 4. So it really goes really very small, very quickly. Okay, so now I'll move to Kelvin waves in a shear background. So now you have like just the Kelvin wave, like the baroclinic equations, and now you impose a shear. It's a barotropic shear to drive the Kelvin waves. And of course, you can do like linear analysis, look at the modes, and you can also do like numerical simulations and see how the waves will interact and how they can excite each other. So we do both. So we take a shear that looks like this, and we force the equations, the baroclinic equations with that shear, and voila. So we do like the linear analysis like Matsuno. You see already the dispersion relations are completely distorted, and also you look at the waves themselves. They look also different. So here I'm just going to focus on the Kelvin wave. So this is like the Kelvin wave you get when you put a shear. And you see this as a non-zero V, as a strong convergence. And these are the pictures taken from a paper by Polarandi 2008, where he looked at Kelvin waves in the Indian Ocean. And they don't really look like the Kelvin waves we see from Matsuno theory. They all have this non-zero divergence in the meridiano. So like, and this is because there are waves that evolve really in the background shear. And I will show you there are also other phenomena like viscosity can actually do that the same.
Unstable waves.
Yes, they can be unstable. Yes, and I'm just skip that part because I'm going to show you in another part. Yes. So this now just trying to see if I run the Kelvin wave and see what kind of waves excite. And you see the Kelvin wave just continues to propagate, but you do excite other waves, mainly Rossby wave, like the first symmetric Rossby wave, and some inertial gravity waves also, and so on. But actually they are very weak when we looked at them. So but only the Kelvin wave that survives, and we look at the structure, it looks like this one we got from the linear theory. And then, but it does excite some waves, but it's not that much. However, if we initialize with a Rossby wave, then now we get exciting, we excite Kelvin waves that are really significantly strong, and also westward inertial gravity waves. So somehow, if you have a Rossby wave propagating from the Eastern Pacific into the Indian Ocean, can actually excite Kelvin waves that will do that.
How do you identify that this is Kelvin wave and not some eastward propagating gravity wave?
Well, we filter it out and we look at how it looks like, and actually from the frequency and
So you are going by frequency for the definition.
Yeah, that's one thing, but also we filter it out and look how it looks like.
So
Yeah.
it's both. So you do spatial filtering and you do frequency and
Yeah, it's frequency filtering. So we just draw a box around this peak and then reverse back to physical space. And then you plot it, and then you will see something like this.
Mhm.
It's a Kelvin wave.
but it will have non-zero V.
Yes.
I see, it's a Kelvin wave, that's the Kelvin wave system without shear inflow.
No, it's not exactly the way. No, it is different. This one will have non-zero V.
If you say this is the Kelvin wave, then you say it's a Kelvin wave without mean shear. So the normal. Because you say the Rossby wave is generating a Kelvin wave.
Yes.
It's a linear system, so there shouldn't be any.
It's through the shear.
Only because the actual wave looks different. And if you project on the linear modes of the system without mean flow, then project something on the.
Well, but then if you project, I mean, you can project whatever you want, right? But these are signals in the spectral peak. But you can project whatever you want and call it what you want. It's a frequency, but here you see them moving as individual waves. They have genuine spectral peak. They are completely separate. I'm not trying to fake it and to project into something. I'm just extracting from the spectrum. I mean, this is.
So I guess the question, also the same question. When you do Fourier analysis of time series,
Yeah.
Fourier analysis in time on these nonlinear signals, you are assuming that the signal will propagate with certain phase speed.
Yes.
Linear time.
No, not necessarily. No, these guys interact. So all these signals you see there, they interact. So all I'm saying is that you start with an Rossby wave, right? It's moving this way, but then there is a signal that it's moving this way, but there is another signal that's coming the other way, moving eastward. And you can, this is not the case like this. I mean, you see this is just a harmonic diagram.
Yes.
You see clearly, I mean, you see it here. That's the Kelvin wave.
For me, I don't know why you call that line R1. I'm not really sure. So when I do.
This is the frequency. This is like the speed of propagation of the Rossby
When I
wave.
do Fourier series analysis in time, I assume that something is some structure
You don't need to
Right.
assume anything.
is propagating with some phase.
You don't need to assume anything when you do Fourier, right? You don't need to assume anything. And then when you see the spectral peaks, then that's the thing that you're after. That's the main signal. But you can see it from the Moore diagram. You can already see waves moving in this direction and in this direction. I'm guiding you with this dashed lines. But even if they were not here, you would see it.
We can talk later.
Yeah.
Definitions.
Yeah, I guess. And that's, here you go. Now we filter the waves, right? When we filter the one I called Rossby wave, that's how it looks like. And that's basically the structure of the Matsuno Rossby wave. And when I filter the Kelvin wave, that's how it looks like. It has a non-zero V. It's not as strong as in the first case, but it's there. And when I filter what I call the westward inertial gravity wave, that's how it looks. They are not the same. So you're not going to tell me that what I call Kelvin wave is a gravity wave. This is a gravity wave. Okay? So what we saw is that Kelvin waves can excite planetary Rossby waves, but then an equatorial Rossby wave can excite Kelvin waves. So it's two different things. But that's through the shear. So there is a shear from planetary scales. Then you have Rossby waves propagating westward. They can actually interact with the shear and create Kelvin waves going east. That's just a mechanism that's possible to trigger Kelvin waves. And of course, then they can become convectively coupled and so on. Okay, I will try to go a little fast. So this is a new work. It's not published yet, just submitted. Just try to basically show you that eddy viscosity is something that can actually be effective in creating some of these interactions. And also, I will talk about mixed baroclinic, barotropic instability, I like to call it, and how this can be important for things like easterly waves and monsoon depressions, and also some structures that look like atmospheric rivers. So I will go slow here, fast here. So this is basically just to convince you that turbulence is important. So there is the instability of the shear that allows the transfer of energy from large scales to small scales. But then, of course, turbulence does the rest of the job through cascades. And like Kelvin Helmholtz instability, that's we know that creates the small scale eddies. But for the large scale synoptic scale waves, we know things like baroclinic and barotropic instability is the one that the ones that drive synoptic scale dynamics. And things like lots of people worked on this suggest like things like easterly waves and tropical depressions come from things like baroclinic, either baroclinic or barotropic. Most people mention barotropic. Some people say it's a mixture of baroclinic and barotropic instability. And things like the equatorial jet or the monsoon trough or the African jet are the ones that drive these instabilities. And there is also the idea that the red noise spectrum that people talk about, like Wheeler Kiladis and so on, originate from processes that are like stochastic, forcing Stockman and Otuvi suggested that there is another paper by Garfinkel et al. Where they think it's actually due to cascades, inverse cascades for mesoscale convection exists as a turbulent cascade in a way. So anyways, but there is also people who think that turbulence in the tropics and subtropics is very, there is ample evidence for it, including in tropical cyclones. There are these two papers they recently came out by Galperin and another by Emmanuel. So we go back to the same model and the baroclinic system and the barotropic, barotropic and baroclinic. Now I'm going to put a baroclinic shear, but I'm going to consider the whole system together. Like we keep the baroclinic and barotropic waves coupled. Like there's a two-way coupling. And then I will add an eddy viscosity term at the end of the equations. And just to make it transparent, the eddy coefficient of eddy viscosity, I write it as a length scale squared divided by some time scale. The time scale is chosen to be like 10 days, which is consistent with what people think is the time scale of like Rayleigh friction and so on. And the LV I will vary. I will just think like, try to think like some eddies that are very small, maybe 5 kilometers, eddies that are larger and much larger, and see how things evolve from that. And by the way, so if I put LV to be the Rossby radius of deformation, like 1,500 kilometers, then you get exactly this dissipation of the 10-day dissipation scale. So I don't need to go too much details, but so what we do is that like the barotropic mode, we expand it in in exponential Fourier modes like that, because it's not trapped at the equator. And then the baroclinic variables are all expanded with the parabolic cylinder functions that are there. And we use what's called as a radiation condition. This, what it does is basically, when doing this, is like effectively projecting into the Matsuno modes. So then you won't get any fake. And then you introduce what's known as the Riemann invariant, basically just transforming the baroclinic equations from U, theta, and V to Q, R, and V. So like that. So this makes it easy to identify the east and west moving waves. And when we do that, so if the viscosity was not there, so if nu was 0, so you get the first equation there for just the Kelvin wave, Q0. And then these two equations will define the ENI or mixed Rossby gravity waves, two branches. It's a system of two equations. And then you get a triad of three equations for Q2, V1, and R0, and also for all, and also Q3 and R1 and V2, and so on. You get these triads, and each triad will have one Rossby wave, equatorial Rossby wave that is, and two inertial gravity waves. But when you have the viscosity, you can see that the Q2 is in the Q0 equation, and the Q0 is also in the Q2 equation. So basically, somehow the viscosity is creating interactions between the different waves or Matsuno waves. Then now these systems are no longer separated into this very beautifully modes that like in Matsuno theory. Instead, you have this much more complicated system. And of course, if nu is very, very small, you can neglect it, and then you get back the Matsuno waves. But is nu really small? And what nu small means? What does it mean for nu to be small? Is it looking at very, very small eddies, or are we, if we think of eddies that are big enough, what's going to happen? So this is just playing around. Now if that's the dispersion ratio, Matsuno when nu is 0, and then you increase nu to 100 kilometers. Now trying to think of 100 kilometers eddies, like mesoscale eddies, like in the Garfinkel theory, then you get almost the same dispersion relation. By eye, you don't really see a difference. And then it gets somewhat distorted when you get to something like 10,000 kilometers. So in the sense that, at least by eye, for reasonably small viscosities, the Matsuno kind of dispersion relation almost is okay. And then we look at the projections. So now the Kelvin wave on top, and then the Rossby wave on the bottom as examples. So when nu equals 0, the Kelvin wave has only Q0. And the Rossby wave has Q2 and R0 and V1. And when you add the viscosity, you can see in the Kelvin wave, even at 500 kilometers, you see almost nothing else. But then when you go like 5,000 kilometers, which means now you have like eddies that are like synoptic scale eddies, whether that's feasible or not, it's a question. Then you start seeing excitations of high order modes. But for the Rossby wave, you also see excitation of higher order modes at 500 kilometers, which is still like mesoscale eddies. And this is now the structure of the wave. So this is now like a Kelvin wave for the strongest viscosity. For the smaller ones, it doesn't really change much. For the Rossby wave, you can already see some distortion here, but then it's very small. So in a way, so viscosity can create some excitations of other waves, but it has to be stronger and maybe too strong. So now we're going to add a barotropic a baroclinic shear, and that's how it looks like. So basically it has a barotropic and baroclinic part, because it's barotropic in the sense that there is a y dependency, and it's a baroclinic at the same time. And this idea of baroclinic, barotropic, or mixed baroclinic, barotropic instability actually was championed by Shukla in the late 70s to explain monsoon depressions as a mixture of baroclinic, barotropic instability. And there are these papers by Youngs and Liang and al, which for this, they basically for the ocean, where they mentioned that some of the mesoscale eddies and so on are created by this kind of instability. So a few things here. So the main drivers, there is the advection of vorticity by the baroclinic mode, and then the baroclinic shear, and then the advection of convergence, and also now this is like a vorticity expression terms in the vorticity equation. So the way it operates is that you have a baroclinic shear, or at least it's a baroclinic shear. It excites first barotropic mode, and then once you have this barotropic psi, then you start seeing an impact in the baroclinic response. So then you get through this advection. And that's how it works. So basically, if you don't have this coupling from the two modes, you don't see this kind of instability. And now without viscosity, that's how the instability looks like. It starts at very small scales. And then it's actually the shear is very unstable right away. And then we have to increase it a little to start seeing some instability at large scales. And when we get some like a value that's more or less interesting, we see lots of instabilities. At small scales, it's a mess. But then if we add a little viscosity, like 5 kilometers, we kill all the high frequency modes because the growth rates are very small anyways. And we start seeing only like the large scale planetary-scale waves. And when we filter these waves, they will look like this. A combination of baroclinic, barotropic. This is completely off equatorial wave that has it's a planetary scale, and it has these elongated strips that look like atmospheric rivers. And then there's another wave that's more closer to the tropics, but it also has the same elongated strips of like atmospheric rivers. And then there are many branches that are unstable, and other branches, and some of them are more tropical, and this we believe like these are more like tropical depressions. And yeah, so am I doing in time?
Yeah, please go ahead. Another
No, I can stop anytime.
Yeah, no, it's very interesting. Yeah. So
okay, so I will probably just talk about moist convection, and then I might not reach to the convective momentum transport, or maybe just show you one picture from that. So I'll try to go fast. So now I'm just trying to include diabatic heating. So for diabatic heating, to understand how waves and convection interact, so people started working with single magnetic mode, just the shallow water system of Matsuno in a way, and then coupling it to what's known as one cloud model, which is just think about just deep convection only. And then the first theories that come up is what's known as wave cisc and moisture convergence by Charlie and Eliason, and then Q. And then there's the adjustment schemes that by Manabi and that's Miller. And then there's the famous Wishy theory by Emmanuel and David Neal. So it turns out all these theories don't explain any of the waves. So the wave disk and the moisture convergence typically lead to ultraviolet instability. There is no scale selection. You don't get instability at the synoptic scales where you want it. The Manabi adjustment schemes are stable. Nothing is unstable. So you have to force them externally to get something going, because this is based on what's known as the quasi-equilibrium theory, where convection is supposed to bring the system back to stability very, very quickly. And then there is the Wishy theory. That's Wishy stands for wind-induced surface heat exchange. So where you basically think of the wind being creating more evaporation on the surface and then strengthening the wave. It turns out this is also not a good theory, because you would need equatorial westerlies in order to excite eastward waves. And that's also not feasible. And then there's the idea of the stratiform instability that was basically introduced by Brent Rapes. And later, this is Maida, not Maja. Maida and Schafter worked on it. So the whole idea here is that you have not just the deep convection, they also have stratiform heating in the top. And so you have two modes of heating, then excite two baroclinic modes. And instead of just the first baroclinic mode, you have also the second baroclinic mode that are coupled through convection. And it turns out this has a nicely scale selective instability, and the instability comes from actually the downdrafts from the stratiform that actually fits back into the boundary layer and then restores builds up the cape again, and then basically has the instability created like that. However, and also the waves themselves look like the waves that we see, convectively coupled waves. They have a tilt and so on. However, when we try to do nonlinear theory simulations, it turns out this stratiform instability in the nonlinear setting is not sustained itself. In the linear setting, it's sustained through an artifact, actually. And I will explain what the artifact is when I introduce the multi-plot model. So, and then basically you end up adding Wishy, and then all you get is Wishy wave when you do nonlinear simulations. I will explain what this means. So this is just to tell you what the stratiform instability is. I said by word, I'm going to skip through. So if we simulate, like we do some global model, a simple model with this stratiform instability scheme, and you force with some SST, like a wormhole, and then you create a Walker cell, like that's the wind's doing, that way, and then going up. And these are the waves. This is just that's the mean, and this is the deviation from the mean. And what you see, like you have here in the region where you have westerlies, you have waves going to the west, and in the region where you have easterlies, you have waves going to the east. And of course, you just see them come back because of periodicity, but they basically are weak there. They are excited here. So basically, to excite waves going eastward, you need actually then the eastward to west. And it's easy to understand, and this is why this is like the Wishy, how the Wishy is written, like the wind-induced evaporation. Like this is the rate of evaporation is written as some constant times some U0, like for turbulent, reference times velocity scale. And then this is the true wind. So this is the background wind, and this is the wave. And then you have this, you need to cooperate in order to, so basically then you get to excite the wave always from the direction that goes to where the mean wind is. So then that's why you get easterlies with eastward waves with westerlies and with westerlies only. So the idea now, how we do that, so because the stratiform is meant to heat the upper troposphere and cool the lower troposphere, and it meant to trail the deep convection. When you do linear theory, you see the suppressed phase of the stratiform comes in front of the deep, and it comes as an opposite signal, which you heat the front and cool the upper troposphere. So in linear theory, it will appear like that. And if you do nonlinear theory, you don't see the phase, the suppressed phase, as being just the negative of the active phase. The suppressed phase means just zero in the nonlinear theory. And so what it does is actually it mimics what's known as congestus clouds in the linear theory. So the congestus clouds are supposed to be in front of the wave, then followed by deep, and then followed by stratiform. And that's how we make and this is just the trimodal nature of deep convection, of organized convection. For many people advocate this. You have congestus cloud, deep, and stratiform. This is like for Kelvin waves, and this is for two-day waves, westward propagating waves. Like you get shallow, congestus, deep, and then stratiform, and so on. And also for the MJO, the same thing. So then we decided to cook up a model where we have like shallow below the inversion, and then you get deep convection when the congestus clouds when the atmosphere is dry, and then it triggers deep convection when the atmosphere is moist enough, and then stratiform will add a deep convection and then create downdrafts that cap again, and then you get a cycle. So the idea is that moisture plays a role in switching between deep congestus to deep. And then we build that into the model. So we have these three heating profiles: congestus, heats below, cools above, deep, and then stratiform, heats above and cools below. And then we project into the two baroclinic modes. You have first baroclinic mode where you see these modes, mostly the deep convection, and the second baroclinic mode we'll see the congestus and stratiform, and then we have a moisture equation in the boundary layer, B, etc., to account for the downdrafts, etc. And then we have this moisture switch, which, if the atmosphere is moist, if it's dry, you get deep convection. If it's moist, you get congestus heating. And I'm just going fast, and then we do linear theory, and then we get this very nice scale selection and stability of waves moving at around 17 meters per second, with growth rates peaking around synoptic scale at 4,000 kilometers away. And it turns out that the low-level convergence from congestus is the one that plays the central role. If we let that low-level convergence to zero, you lose that scale selection, you get the instability of waves that actually are not moving. That's almost like the wave disk. So this congestus mode creates low-level convergence, and that low-level convergence moistens the lower troposphere, and you get deep convection. And that's the main mechanism for these waves, and this is just how the waves look like. They have the tilt and everything. And this is now when we do the simulations, as we did for the stratiform with the warm pole, the same warm pole as for the stratiform. Instead of getting waves moving here and here, now you get waves in the warm pole, like the Kelvin waves moving, just like you see it in the real world. So here, just zooming on that warm pole, you see these waves moving at like 16 meters per second. You also see some envelopes moving in the other direction, but I don't have any time to show you all this. This is another simulation where you see some envelopes moving like some kind of Madden-Julian oscillation, and you see the Kelvin waves moving at at 17 meters per second. So this is when we put this parameterization in CFS. This is the NCEP model. So we do get a very nice looking spectra as like so this is from NOAA 1R, that's the observations, and this is the default CFS, and that's the CFS when we put this parameterization in it. So you get the less signal of Kelvin waves and better MJO, also better Rossby waves, and most importantly, get the westward inertial gravity waves as well. And we get some of the MRGs. And then we look at the filtered MJO from both the default CFS and from the SMCM, what we call the stochastic multi-cloud model simulations, and then from the observations in the center. This is the MJO, this is the lower troposphere, this is the upper troposphere. You get the gyres, the 4 gyres, and then you get the heating in the middle, and that's what you get from the stochastic model, and that's what you get from the default CFS. So the default CFS has an MJO signal, but when you filter it, it doesn't look anything. And I think probably I should stop here. So just to show you like the pictures from the MJO propagating from the stochastic model, the multi-cloud model from observations, and that's from the CFS. Thank you.
Thank you very much.